Hi roboticist, today we're going to be talking about checking self-collision using MoveIt. And what we're going to do today is to write a ROS node that is able to check if a robot, or better our robot, is hitting itself, or better a link of the robot itself in a certain configuration, or the robot hits an object that is present in the scene of our environments. So this will be very useful when you are going to develop a robotic application, because you want to check if the end effector at the target position could hit something. And in a pick and place application, you want also to ignore a collision with the object that wants to be picked, of course, because it has to grasp the object itself to pick and place somewhere else. Okay, before to dive into it, make sure to subscribe to the channel, hit the bell, the notification bell, in order to do not miss the next topic. And if you want to make a deep dive in robotic application, you can check the course that I have created. It has been created for beginners for the moment, and the advantage is that if you're gonna take this, you are gonna benefit of a one-to-one discussion, let's say one-to-one coaching of my time to help you out in deploying your robotic application. And the advantage to take this course is also that you can download the video and watch them whenever you want. So what we can do is to run into our directory where our cobot test package has been made. And if you don't remember, I'm gonna put the link of the package that we have created here. Okay, so as a recap, what we have done so far in this package is to create is to use the move group interface, where we have asked the robot where we have asked the robot to go in a random position, then in a custom position, where we are gonna place the end effector in a certain position and orientation, and then we have seen how to add a collision object in our scene and how to attach and detach that object to a certain link. All this video, all this C++ node has a video associated, and you can check out in my channel. And something that you need to do, make sure to have your MoveIt configuration package done of your robot. I'm gonna put the link that is popping up now. So now what we can do is to go here in our source folder and create another file, and let's call it checking collision. So first of all, what we're gonna do is to include the libraries that we need. Here you are. We needed to include the robot model loader, the planning seal, and then kinematic constraint utils and Engen message. We are gonna use it in a while. Then let's create our main function. So now, as we did in the last video, we need to instantiate and create a node and give it a name, and then add the spinner and start. Here we go. Till now, nothing new. So now what we need to do is to load the kinematic models of our robot to the planning scene, and this is getting from the robot description parameter that has been created automatically from the MoveIt configuration package of the robot that we have created the URDF file. I'm gonna put the link in the description. Here we go. We load our robot model, we get the model, and then we're gonna place in our planning scene using the class that we have included here. Then what we need to do is to do the collision checking. So what we're gonna do to test the self-collision in the current state, that as default all the joints has 0 angle, we can create 2 instances of the collision detection, collision request, and collision detection and collision result classes. And we're gonna name it collision request and collision results. So let's do it. Here you go. These are the objects that we just talked about. And then after that we have created this object, we need to pass them to the planning scene check self collision. So planning scene, we are gonna use these classes and this method, self collision function, and we need to pass the request object and the result object. Okay, then we can display to the terminal if this configuration brings us a self-collision, meaning that we have some links that collide with each other. So we are gonna do it using the ROS_InfoStream function. So here we go. We are gonna ask to the collision method of the collision results class to give an input if it's in or if it is in not self-collision here. So we can test it right away, and we could shut this down. So ROS shut down. Okay, this is very simple. So how to test it? Well, first of all, we need to go into our CMake list text file, and we are gonna ask CMake to create an executable file from this text file. So we just need to copy and replace the file cpp C++ file from which we are gonna create the executable file, and it's gonna be checking collision and so on and so forth. Okay, the package has been built properly, and what we need to do to check this is to launch the MoveIt configuration launch file, where we are gonna use the demo launch file as we did in the last video. As we imagined, the robot has been spawned in our scene of RVs where the joint have all the 0 degrees. So it will not, it's impossible to make a collision in this configuration. So what we are going to expecting is that the string will be test1 self-collision test, not in self-collision. So we can run this node, open a new terminal, and let's run it. And as we expected, test 1 self-collision test, not in self-collision. Why that? Because the collision method belonging to the collision result class, which is an object instantiated from the collision detection collision results classes, says that it is not in collision. So that's all for this first test. Let's raise the bar and let's put the robot in another configuration where we are sure that it will collide. So to do that, first we need to get the current state of our robot. And we are gonna use the robot state class, and we are going to instantiate an object belonging from this class that we can call it current state. That it will be equal to the planning scene get current state non-const. So we are gonna call the function get current state non-const from the class's planning scene. So now let's create a vector that has all the joint values in radians. So since that we have 6 joints, we are gonna create a vector that we name joint values, and passing to that vector all the joints that we want to have as a configuration. So I remember you that as of now the robot has all the angles as 0, so it will have the following configuration. So after that we have created our vector that contains all the angle of the joint of our robot. We will need to pass it to the model of our robot, and to do that we need to instantiate an object belonging to the joint model group. So let's do it. So to the current state object, we are gonna use the method getJointModelGroupArm that we have created in our MoveIt configuration wizard, and all the joint model group is contained in this object. And then what we're gonna need is to set the joint group position, passing to that method the joint model group and the joint value, like this. Here you go, the robot state object. We are gonna call the set joint group position method. So here we need to pass the joint model group that we have created and the joint value. And now finally we can check if the robot goes into a collision or not. So, but this time, instead of calling the collision method of the collision results, we are gonna ask the satisfied bonds belonging to the current state classes instantiated, and we're gonna pass the joint model group. And basically we'll do the same function as before, but with the difference that it will check if the angles that we have set up here as a joint value could interfere with the limit of our robots. So of course it will not, because the angles are at 0, so we are good. So if we wanna test it right away, we can do it. So first of all, you need to build the package again. And here you go, we have the test of before and we have test 2. Current state is valid, of course, because we didn't change any angle here. So what if we set the angle of the link 2 and link 3? For example, I remember that it's gonna be a limit. No, not this one. Should be this. So here, for example, you can see that this has a limit of 133 degrees, and most likely if at the second position of this joint we are gonna put a greater joint value in radians, for example 3.14, so that is corresponding to 180 degrees, we should see that this will not be valid. So let's check it. Build the package again. And in this case, what we should expect that this satisfied bond functions passing the joint model group should respond as a request that is not valid, because the second joint cannot reach, due to the URDF limit constraints that we have set up, such an angle. Okay, let's check it right away. And here we go. Test 2 current state is not valid because this second cannot go up to 180 degrees. So that's why this returns this output, and this is very useful because if you want a particular joint go in a certain position and you don't want to check your RDF file, the limit of the joint that you have put or is given from an external package that you have just downloaded from GitHub, it is always useful to check with these few lines of code. So let's raise the bar a little bit and let's put another joint angle here, and let's see if we have some link that collide with each other. So what if, for example, we are gonna put this joint angle to 180 degrees? You can see here that we have at this configuration the link 2, which is this one. This one is the link 2 that is hitting the link 4 and link 5. Here, this is the link 4 and the link 5. So remember, base link 1, 2, 3, 4 and 5, and in this configuration this and this will be collide with this. Okay, because it's turning red. Okay, so let's check it via a script, and the response will be a string that will say, hey, with this angle you have the link 3 that is hitting link 4 and 5. Let's do it. So as I mentioned, what we can do is that we can get contact information for any collision that might have happened on a given configuration. For example, 180 degrees for the second joint. And we can ask the contact information by filling in the appropriate field in the collision request and specifying the maximum number of contacts to be returned in a large number. So, for example, we can specify the collision request contact to be true, like this, and then specified the maximum number of contacts that we can set up as 1000. Then, to be sure that the collision result object in this test doesn't affect the result from the previous one, you could clear it. So we just need to ask the collision results to be cleared just by calling the method clear. Okay, and then as we did in the test 1, we can ask to the planning scene class, and in particular to the check self collision method belonging to this class, to check the collision, and I remember you that we need to pass to this object the collision request and the collision results. So here with this object we are asking to the planning scene class if the configuration that we have set up is colliding somehow, and the collision result is an object that contains this information. So this kind of output that we want to be printed in the terminal is equal to the one that we have set up in the test 1. And okay, now what we can do is to iterate through the maximum number of contacts, and we are gonna check if some links might be in contact with each other with this configuration here, and we know from our RVs that it is. I remember that the link 1 the link 2 will collide the link 4 and 5. So this will be the output of our test 4. And here we go. This is how you can do it. So you iterate through the begin and to the end of any contact that might happen through all the links, and you're gonna display what will be the first link that is contacted to the second one, and make this for all the combination that you might have in your robots. Okay, so first let's remember that you need to change this angle to 3.14, that is gonna be 180. That's this is this configuration here. So build the package again. And as you can see, we have the output that we were expecting, because at this link 2 and link 3, that is gonna be this one, this joint here, if it's gonna be 180, so we have the link 2 that is hitting the link 4, and the link 2 that is hitting the link 5. And I remember you that this is the link 2 here, this one, and the link 4 is this, and the link 5 is this. In fact, they are changing the color here in this position. So something that I wanted to point out is that here is happening something strange. So during the pathway to go to the target configuration, you can see that we have another hitting here. So we have a hitting of this link to the link 1, but in the target position the hitting there will not exist. So pay attention to this, because this method here has a drawback that cannot tell you whatever in this pathway, path planning, let's say, there will be a hitting of some link between each other. So pay attention to that. So now what we're gonna do is to modify the allowed collision matrix. First of all, what the allowed collision matrix is? This is belonging to the class collision detection, and it provides, let's say, a mechanism to tell the collision word to ignore collision between a certain object. And if you think it's very useful when you need to go with a pick and place application, because you want of course that the gripper of your end effector may make a collision with the pieces that you want to pick, right? So both part of the robot and the object in the world has to be taken into account in this allowed collision matrix. That for this particular case has to be ignored. So we can tell the collision checker to ignore all collisions between the links reported above. And in our case it will be the link 2 that is hitting the link 4 and the link 5. So let's do it right away. So first of all, we need to instantiate an object from the class collision detection allowed collision matrix, and we can call it ACM, and this is equal to the planning scene, and then we are gonna use the method get allowed collision matrix. You can use the help of the autocompletion. Okay, then we need to copy the robot state. So we are going to instantiate an object of type robot state, and this is equal to the planning scene, and now we use the method get current state. Okay, now we need to iterate through all the collision that we have, and we place all these collision in the object ET2. So basically it's equal of what we have done before. So to keep it simple, we just can copy the for loop and update the const iterator object instantiated just before. And then actually we need to ignore this collision instantiated in the IT2, or better stored in the IT2. So we need to call the object set entry, and then we are gonna use the pointer to the first and second, and this is gonna be true. Then what we need to do is to clear the collision results. Otherwise, the collision result is going to affect the test 3 that we have done before. And what we can do, as we did in the test 3, we can check the self collision. So we are gonna use the method check self collision belonging to the class planning scene that we have instantiated. And we need to pass as an input, as always, the collision request, the collision results, and the copied state. And of course we need to pass the ACM. Then what we can do is to print on the terminal if we have a self-collision now, after that we have modified the allowed the collision matrix. And so basically there's nothing new here. We can call it test 5. Okay, now everything is set up and we could test it out, but first of all we need to build our package. Okay, it's done. Then launch the demo launch file of our Cobot MoveIt configuration package. Wait until RVs is loaded, and then you can, as always, open a new terminal and run the node check collision. And if everything is working good at the test 5, we should see that there is no collision, even though we have set up a configuration where the link 2 is hitting the link 4 and 5. Let's test it. So run Cobot test the package and then the node check collision Cobot node. Let's run it. And here we go. You can see here that in the test 4 we have a collision between the link 2, link 4 and link 2 and link 5, but in despite of that, the fact that we have modified the allowed collision matrix allows us to detect this configuration as not in collision. Okay, as a final test, what we can do is to make a full collision checking. So what does it mean? It means that while we have been checking for self-collision, what we can do now is to use the check collision functions that we have seen so far, instead, which will check for both self-collision and for any collision that might happen in the environment, with, for now, as you can see, is currently empty. So this is the set of collision checking function that you will use most often in a planner, because you need to check if the robot is in self-collision with itself and with other objects in the environment, and there will be another case that you want to ignore a specific collision if, for example, you wanted to pick a certain object. To do that, you need, of course, to clear the collision results, and then now we are going to create another object. So we need to instantiate an allowed the collision matrix object, and we can call it ACM2, and this is equal to the planning scene, and we're gonna use the get allowed collision matrix, so as we set up before.
So basically here we just make the same things as before, with the exception that we want the check collision with the new object instantiated ACM2, and finally we can print on the terminal what is going to happen just by using the rowinfo_stream function. Okay, build the package again and then test it out again. Run the node. Okay, and now you can see that from the test 6 the robot is in collision, of course, because it's not ignoring the fact that the link 2 is hitting the link 4 and 5. So everything is working correctly. So if we are gonna make the test 6, it tells us that we have a self-collision in this example, or in general a collision. Okay, so what we can do now is to put an object in the scene and check if the robot is in collision. And to do that, what we need to do is to create on the scene an object like a cylinder, a random one, and we have done it something similar in a video before, where we have spawned a cube. I'm gonna put the link in the description down below. So what we can do is to just copy and paste the part of that code that we have just used it. So this is something that we have created in the file attach detach object cobot. And to do that, I remember you that we need to create a current scene that belonging to the planning interface, planning scene interface class. And then we need to instantiate a collision object, and we are gonna do a cylinder, and then we're gonna put a cylinder ID. We can call it a cobot cylinder, and then instantiate a shape message primitive, a type that is gonna be a cylinder, and then put some dimension that describe a cylinder itself. And then what we need to do is to give an orientation and a pose to the collision object cylinder. And as an example, just put it at the center, in a place that we are certain that the robot is going to collide. So let's put it in 0, 0 and 0.4 in Z, and then you need to, let's say, spawn in the scene this primitive shape. So just copy this piece of code that we have created last time, paste in our code and adapt it for the object cylinder. Then I remember you that before to test it you need to import the key libraries that we need to have if you want to use the planning interface classes. So you just can copy the one created in the attach object cobots and paste it in our checking collision code. Okay, now everything should be ready. And build the package again and test it out. And here you can see that from the test 6 it appears that after the full collision test we have a collision. So the test 6 detects that we have a collision only in the cylinder part. So from the test 6 we can see that despite the fact that we have a collision of the link 2 and the link 4 and link 5, we are going to ignore that thanks to the test 5. And in the test 6 we detect a collision between the new configuration of the object and the cylinder, because we have used in the check collision function the modified allowed collision matrix. So that's all for today. I hope that you enjoyed this video. If you like this video, don't forget to subscribe to the channel, hit the notification bell, and if you wanna have a deep dive in ROS, you can check the course created for beginner. I'm gonna put the link in the description down below. So thanks for your attention, and as always, keep learning robotics with ROS.